be giving a more broad overview of dark matter and collider searches, with some emphasis on a few examples that I worked on. So let me begin with just a statement that dark matter, just some few statements about dark matter. So the past few years have been a pretty interesting time for dark matter. For one, we now know how much dark matter there is to very high accuracy. So this is a picture of the CMB, of course. Last year, Planck observations of the CMB have allowed us to pin down the average density of dark matter to within a few percent accuracy. And this average density of dark matter has historically been a very tantalizing number for particle physics. The reason is because of the WIP miracle, basically. So there's some average density left out, or left today, and that could be explained by a massive particle in the early universe which annihilates and freezes out. So the idea is there's a massive particle which is in double equilibrium. It can annihilate to standard model particles, so its number density is dropping with temperature, but eventually the annihilation can no longer keep up with the expansion of the universe, and so this number density will freeze out and give some relic abundance of the dark matter today. And the WIP miracle is the statement that if you take a, say, weak scale dark matter particle, weak scale annihilation cross-section, this is in the right ballpark to get you the relic abundance observed today. So this WIP miracle has led to lots of different searches for weak scale dark matter. For example, direct detection has also been an exciting field the past few years. This is a picture of Lux, which last year gave the strongest limits so far on the WIP nucleon scattering cross-section, where the idea is that if you have a weak scale particle, it can scatter off nuclei, leaving a very faint signature in the form of nuclear recoils. You can observe those nuclear recoils if you have a very low background, low threshold experiment, as your target is passing through the wind of dark matter particles. You can see some occasional scatters. And so that leads to these constraints on scattering cross-section versus mass in this target range of 10 to hundreds of GeV. You can also look for 100 GeV scale dark matter particles by looking for indirect detection. So these particles can annihilate, and that will give you GeV or higher energy gamma rays. And you can look for those on the sky in regions where you expect very high dark matter density, for example, with the Fermi Gamma Ray Space Telescope. So what does the LHC have to do with all this? So before I give the motivations for looking at dark matter at the LHC, let me briefly summarize for anyone who doesn't think about the LHC. So the LHC started off a few years ago. The first run was 2011 to 2012 at center of mass energies of 7 and 8 TeV. Of course, we saw the Higgs discovery with the first set of data, which was 25 inverse femtobars. And the LHC will start up again next year, center of mass energy 13 to 14 TeV. Expected data is a factor few higher than we've seen so far. And so the hope is with this increase in energy and luminosity, we might be able to start probing SUSY or dark matter or whatever else. So let me give a few reasons for thinking about dark matter at the LHC. The first has to do with the WIP miracle. So I've already tried to motivate the idea of looking for dark matter which has a mass in the range of hundreds of GeV. And if you're looking for these kinds of particles, the only way you can produce them in the laboratory is if you have a very energetic experiment. And so you should really think about the LHC. It's the only experiment currently running that can really produce 1 TeV dark matter particles. In addition, if dark matter can annihilate to standard model particles with weak scale cross-section, there could be other new weak scale physics associated with this dark matter. And if you want to probe that physics, again, the LHC is where you want to do it, because you could have heavier partners to this dark matter, and to really explore all these interactions with other new weak scale physics that you want to think about LHC physics. independently of the idea of the WIMP miracle, looking for dark matters at colliders is also important from the point of view of complementarity. So this is the idea that if you want to convincingly detect dark matter, you want to do it in a number of ways. So this is the complementarity diagram. The idea is you have some interaction of dark matter with standard model stuff. And by turning this diagram on, or looking at this diagram from different ways, you get different ways of probing this interaction. So you have dark matter annihilation to standard model stuff is indirect detection, the scatter is direct detection, and pair production of dark matter in a collider. And because any signal in a signal in any one of these channels is usually very difficult to say is dark matter, it's important to do it as many ways as possible. Okay, so that brings me to the subject of my talk, which is some new directions or some recent developments in the field of thinking about dark matter at the LHC. So I'll start with a discussion of looking for contact operators and monojets. So this is so these new directions are really bottom-up approaches to thinking about dark matter. One of the simplest things you can do is look for contact operators. In this case, you assume that dark matter is the only new particle relevant at the LHC. And you've integrated out the heavy physics, and you're just left with some operators. And then you can generalize this a little bit by looking at simplified models. And here, the dark matter can be produced, but there are also possible additional particles that could be produced. But rather than going to the whole, specifying the entire UV theory like Susie, you just look at a simpler model with just dark matter plus one or two additional particles. So these monojet searches started a few years ago. The idea is we can pair produce dark matter at the LHC through QQ bar interaction, for example. The dark matter is invisible in the collider, but you could tag this event if one of the quarks in the initial state radiates a hard gluon. So this will give you a hard jet plus missing energy, which is why these were called monojets. So this interaction here, the pair production of dark matter, is described by some contact operator. You can study these contact operators in a generic way or in a systematic way by just assuming dark matter is a standard model gauge singlet, and then you can write down all the contact operators that might be relevant. Looking at contact operators is also good from another point of view, because there's there's something nice about it, which is once you write down this contact operator, you can write down what the collider signal is. You can say what the direct detection signal is from that same operator, and you can also compute the relic abundance. So it illustrates the idea of complementarity very well. So here's an example plot of a monojet event. So there's the single hard jet with the missing energy going the other way, with typically 350 or 500 GeV in the Atlas case of missing energy. And the right side is the spectrum of monojet events. I put this here, one, to illustrate that the dominant background now is the Z plus jets. So the black dots are the data, the orange is Z plus jets. And it's really nice because, I mean, by now, missing energy is very difficult to measure, to pin down. So, I mean, lots of things can fake missing energy. But you can see from this plot that there's actually very nice agreement of the data with the irreducible background of Z going to neutrinos plus jets. So they've really been able to cut down on mismeasurement and other kinds of sources of fake missing energy. The other thing I want to point out with this plot is that, so you can see this is a steeply falling function of the missing energy. For the background, the same is also true for the signal, which is given by these dotted lines. So monojets are looking at monojets are a nice way to constrain dark matter signals. It's a little more difficult to say you can detect these because the signal and the background are both steeply falling. So there are ways of going forward from this, potentially, but monojets are difficult for detecting dark matter. So this also motivates the idea of complementarity, right? So if you saw anything here, it wouldn't be necessarily convincing that it's dark matter.
Is there, could you remind me which operator is D5?
D5 is the axial or axial vector. I can't remember.
Oh, okay.
Exactly which. Oh, actually, here. It's the vector. Okay. So you can go through and from this monojet data constrain lots of different operators. So this is a slide of some tables of operators from this paper. I put this here to illustrate the fact that you have a lot of different choices. So you can go through as many tons of operators by just saying, is your dark matter fermion or scalar? Is it real or complex? Beyond that, you can also ask, what is the precise structure coupling the dark matter to quarks? For example, you have scalar, vector, and so on. You can also couple dark matters, in addition to quarks, you can go to gluons and other particles, but this table just has quarks and gluons. And coupling to gluons is also very relevant at the LHC, for example. So each of these operators has a coefficient, but in general, they're all contact operators, so they all have a 1 over mass scale, 1 over a mass scale to some power. And so by comparing the monojet data with your prediction, you end up with these kinds of limit plots on this mass scale of the operator and the dark matter mass. So the constraints are fairly constant at low dark matter mass, simply because the production is insensitive to what the mass is down here from below hundreds of GeV. And they cut off here because you no longer have the kinetic, you just don't have the energy to produce GeV dark matter pairs. So your signal is much smaller. For most of the operators, the constraints are on the order of a few hundred GeV to 1 TeV in this mass scale. In general, these constraints are not very sensitive to the specific tensor structure that I mentioned. However, they are, you do have to do something different for these kinds of, for certain operators where you have an additional mass of the quark appearing. And so I'll discuss that more in a moment.
So the thermal relic thing, to be a thermal relic, it has to be...
Yeah, that's the green line.
Oh, that's the green line, okay. What's this thing down in the...
Oh, this one?
Yeah.
This is a unitarity constraint. I think it's it's where some if you insert the coupling and the mediator mass, I think it's where the coupling reaches the 4 pi or something.
So anyway, to be a proper thermal relic, you have to be above the green line or to the left. That's
Yeah, so this is the thermal relic, and right, if you're below it, you're just going to annihilate away completely. If you're above it, you just need some additional channels to so that you can get enough annihilation to get the right resistance. Okay. So these constraints are then mapped onto the dark detection plane. That's the other advantage of these collider studies. Because they're insensitive to the particular structure of the operator in many cases, they can do well over, very well compared to direct detection. So if we look at all these operators, not very few of them actually have direct, a unsuppressed direct detection cross-section. So those are the red ones are spin independent and green ones are spin dependent. The others will all have, for example, velocity suppressed with nucleon scattering cross-sections. And so mapping the constraints in the mass scale for the contact operator into direct detection gives you these kinds of limits. So now this is the scattering cross-section for direct detection. And these are you can compare them to the current direct detection limits. And so this leads to the statement that people make about LHC monojet constraints, which is that they're most powerful for low mass. As we saw, the limits don't really change for low mass, whereas for direct detection, they rapidly die off below 10 GeV. And they're also very effective versus for spin-dependent scattering, where for direct detection you don't have the same coherent sum over all the nucleons. So the direct detection limits are comparatively very weak, whereas the collider constraints, it doesn't really matter whether it's spin-dependent or spin-independent. Okay, so that's the main monojet story. There will be some important modifications to this. But what I want to do is now discuss monotype searches some more. So in addition to monojets, it led to a bunch of mono other stuff work in recent years. So the way this goes, I guess, is you can just take the standard model and you append mono to every particle in the standard model, effectively. So we start with mono. Well, except for neutrinos, yeah, that's not very useful. So we started with monojet. That could be distinguished actually between monoquark and monogluon if you can do some quark versus gluon tagging. You can also distinguish light jets versus heavy quarks. So I'll talk more about mono B. There's also monotop you could look at. You can go through the gauge bosons and have mono photon, mono W, mono Z. There's also mono lepton, which I didn't list. It could either be a real mono lepton or mono Z. Mono W also gives you mono lepton. And then, of course, we have the newest confirmed addition, which is the Higgs boson. So I'll mention mono Higgs as well. So a lot of these are all, so as the name suggests, they're all whatever particle this is plus missing energy from the dark matter. In addition to this, there's also been work in the monojet field, essentially, which involves higher order correction. So monojet, I should add, is a misleading name because a lot of the times you do have additional jets being produced. The actual search does allow additional jets. And so these things, the Razer analysis and higher order corrections take that into account. Okay, so let me talk about mono B, or mono B jets. So this is really relevant for certain kinds of operators which have this scaling of the coupling of the dark matter to quarks with the mass of the quark appearing in the operator. And the reason that appears is just, it's simply an assumption, but it's an assumption which is coming from minimal flavor violation, which allows you to get around the fact that if you put in some new scalar with just generic interactions, this could potentially lead to strong constraints from flavor observables. So the simplest thing you could do is just put in a Yukawa interaction here, or that appears as the mass of the quark. So this leads to the fact that you have very weak coupling of the dark matter to light quarks, and that means the traditional monojet analysis doesn't actually work that well for this kind of operator, because that's really probing, that's really looking for couplings to light quarks or gluons. So what we studied in this paper was just a simple modification where we looked at what the signal was for producing dark matter plus heavy quarks. Heavy quarks can be tagged, so that can really help you improve the bounds on this operator. So for example, in this case, if you look at you can get a mono B signal if you have, for example, gluon B in the initial state produce dark matter pair and then a B goes out. Or you can pair produce, you can have gluon splittings into BB bar pairs, and there you can get 2 Bs plus dark matter. And so even though the rates in general you would expect to be smaller because you need to have gluon splitting into heavy quarks, or similarly you need to have a B quark in the initial state, this suppression effectively of the B quark PDF of the proton is made up for by the fact that you have this much larger coupling to B quarks. So in this case, for the scalar operator, we get a much larger signal from looking for states, final states with B's plus dark matter. This search helps in an additional way. But by going to the monojet analysis and you're requiring a B tag, you're also cutting down on the backgrounds. So the B tag efficiency is fairly high, so that means you keep most of your signal. But most of the background was from Z plus jets, and those jets are mostly coming from light quarks or gluons. And so if you require this, you're also cutting down on your background by 2 or 3 orders of magnitude. So now actually your background is coming mostly from things like tops, where you get lots of heavy flavor in the final state. So the reason I really like this is because although it's just a simple modification of the monojet search, it just wasn't looked at. I mean, all the monojet data was there, but people didn't just apply a B tag and see what came out. So this is just a new signal region. The atlas analysis of this is in progress. We've also talked to some CMS people. But this one I know is definitely very much in progress. And so it's just looking at data that's been sitting there and seeing what can we do with it. So in terms of the limits, this is again the contact operator scale and the dark matter mass. It leads to a large improvement in those limits from 30 GeV this is from the Atlas 7 TeV run, and this is the projected limit with this mono B search. So it leads to a factor of 3 improvement or so. And if you map then the direct detection plane, that looks even more impressive because it brings you down 3 orders of magnitude. That's because of the scaling of this direct detection cross-section with this mass to the 6th.
So dot is low. No, I'm joking.
The Higgs were responsible for this operator.
Yeah.
And it has 100 GeV mass. Does that mean that M star would be 100 in this formula?
It's similar. Yeah, it's around 100. But I think in the
Then you
Higgs,
have this pole business that
Yeah.
changes things. So is this really consistent, I guess, is my question.
that's right. This in this case you do get, yeah, it's very similar to the Higgs mass if you map this into the Higgs exchange, but we assumed contact operator, and so it'll change quite a bit. I guess probably the most important change is that you're not, this is no longer an upper bound where you're going to exclude some range of couplings to the Higgs. But it won't look exactly like this in this plane. Did you?
No.
Okay.
I mean, this contact interaction stuff becomes more accurate, actually. I mean, if you were thinking of this contact thing as coming from some exchange, right, then you'd really have 2 parameters. You'd have the mass of the particle that's being exchanged in the coupling. Right?
Yeah.
And this contact interaction thing becomes more and more correct as you increase the mass of the particle and increase the mass of the coupling to keep the contact thing fixed.
Yeah.
And so I would guess in the Higgs thing, where the coupling is very small, this would be totally
That's
totally
what
not
I'm saying,
accurate.
yeah.
We'd actually get much stronger Higgs strengths.
Well, I think it's weaker.
Well, sorry, sorry.
Sorry, yeah, for the Higgs, if you assume that the mass is the Higgs mass, okay, we looked at this at some point, and sorry, the thing I was saying before was that you get a range of masses. For a range of masses and couplings, you get exclusion. And I can't remember exactly if you take the Higgs mass, what are the ranges of the dark matter to Higgs coupling that are excluded. But they're
Your
order
operator
of 1.
had, your operator had, I mean, it depends on, of course, it also depends on the Higgs coupling, what you assume about the Higgs coupling to the dark matter, right? So,
Right. So yeah. There's an upper bound on the a lower bound on the coupling of dark matter to Higgs, which is order 1, if I remember. I mean, it's fairly large. So there's also a dark matter coupling to tops, which is even larger than the top mass. And if we assume this exact form of the operator, you also get a factor of 10 larger cross-section from TOPS plus dark matter production compared to mono B. So we looked at that as well. And the only thing I want to say here is that in this case, you can improve this limit even more. And an additional thing that's kind of interesting about this is that by doing these kinds of searches, you can start, if you were to see something, it would be very interesting to probe how dark matter is coupled to different flavors of quarks. That could be very informative,
So do
potentially.
you get this from semi-leptonic tops, or what? Like, where does the best constraint come from?
The one we did was all hadronic.
All hadronic.
And I think they were comparable. We didn't try to optimize it too much because these are just projections. So. Okay. Those were projections for 8 TeV. You can also look at the 14 TeV projections with 300 inverse femtobarns, a femtobarn of data, and that goes all the way down to this blue line. The thing I wanted to point out here was that this is kind of interesting because there's been some recent excitement in the direct detection field with all these blobs representing fits of data to dark matter, fits of signals in direct detection data to dark matter scattering. They're quite controversial, but if you take this region and maps roughly onto here, and so the idea is, at least in this case, you have a collider probe of models that could explain this, of a model that could explain these typical cross sections. Okay, so that's mono B. The next thing I want to do is mono Higgs. So this is a paper that should appear quite soon. There's also been some other recent papers about this. So the idea is simple. It's that we found a standard model like Higgs. There's a new particle. So that's potentially a new signal channel for looking at dark matter, or a new way to probe dark matter interactions with standard model stuff. So now the question is, what are we actually probing, or are there some things, or some models we can write down that have these interactions? So there are lots of ways to do this. This is just a slide showing some example diagrams studied in one of these recent papers. You could have you could have like Higgs portal coupling to dark matter. So there you could go through a Higgs to Higgs plus dark matter. The one I'll be focusing on is a Z coupling. So you have dark matter coupling to Z plus Higgs, and you produce the mono Higgs through the Z. And you also have these other more complicated higher order interactions, higher dimension operators. So what kind of signal is a mono Higgs? This depends, of course, on the Higgs decay channels. One way we could look for, we would look for a mono Higgs could be Higgs to BB bar. That has the largest branching fraction for the Higgs, so that would keep most of your signal. And that signal region is actually covered in the recent Higgs searches. So, for example, this is the V plus Higgs analysis. So there you just have a Higgs plus missing energy signal simply from a Z going to neutrinos. And so this is very useful for limit setting, or we found it was very useful if you want to set limits with the 8 TeV data, because you're keeping most of your signal, and because this analysis just exists. However, it's not as clean as looking, for example, at Higgs plus diphoton. The branching ratio is very small, so we get, for at least the cases we looked at, it wasn't to our advantage to consider this channel, but if you go to 14 TeV data, this could potentially be very interesting. So this signal region of 2 photons reconstructing to the Higgs mass plus missing energy is just currently not a signal region for LHC searches. So this would be a very remarkable thing. A very remarkable signal if we saw it. And so that's another motivation for thinking about mono Higgs. if we can come up with some reasons to study dark matter couplings to Higgs, this could be very interesting for 14 TeV. And this was also studied in a recent paper by Linda Carpenter and others.
So that point that around 100 GeV on the left-hand plot has an excess above your backgrounds. Which I guess it's maybe 1.5 sigma or something.
Yeah.
Like that. Did the experimentalists commented on in any way on that?
Not that I know of.
I mean, it's sufficiently close to the actual Higgs mass that you might wonder if it could be something.
Yeah. Yeah, I guess the interesting thing is that, so this is more like, well, 125 is closer to this one.
Yeah.
So it does look weird because those two bins are both in excess, and the one that's closest to the dark matter, so this is the one that's closest to the actual Higgs mass, which is the red one,
Yeah.
is all here. So the number of observed events is actually a little too low.
Yeah, right. So the experimentalists only know what the reconstructed mass is. Fairly
Yeah.
accurately.
Yeah, I guess, I mean, that's one of the reasons that this one doesn't look as it doesn't look as nice as the diphoton, because the mass reconstruction is much more difficult. So those are potential mono-Higgs experimental channels. Let me describe some cases where you might produce mono-Higgs. So let me just preface this by saying I think these are ugly operators, but I also want to use them to illustrate a point about the effective field theory analysis of dark matter, coupling to dark matter colliders. So the reason we were focusing on production of Higgs plus dark matter through a Z is because we already know that making Zs is pretty easy. If we were to make this in Higgs, that would be much harder. So we just went with Zs because that's where we saw the promise for the largest cross sections. Okay, so you go through the same procedure as before when you write down these contact operators. You assume dark matter is a gauge singlet. It has to couple to a Higgs doublet. And then to get something gauge invariant, you need something else. And so that's where the Z comes in. So here's some example operators that we found that could give this. They're all very high dimension because it is somewhat difficult. We don't have to focus on the specific form of these standard model parts. They all involve derivatives, field strengths, and Higgs. But after putting in the Higgs values and expanding out, basically they all give some coupling of Z and Higgs, maybe with a derivative.
You didn't consider dark matter being part of an electroweak multiplet?
No, not in this case. Yeah.
Suppose the constraint is stronger?
Sorry.
Just because the constraint would be stronger? Or
Yeah. Yeah. If it's in a multiplet, then the constraints presumably would be stronger, and also you already get a lot of operators this way, so this was the first step to assume it's a gauge singlet and see what you get out. So you get a lot of operators. They're all high dimension. They're not terribly nice, but you can go through and calculate the mono-Higgs signal, compare with the BB bar plus missing energy channel I showed, and get some constraint. And again, this is the same mass scale versus dark matter mass. And this was for the dimension 8 operator I showed with fermion dark matter on the previous slide. So the reason I'm discussing these operators is because if you look at the naive limit, it's above 200 GeV in the scale for this contact operator. And so this is kind of ridiculous because I'm talking about a dimension 8 operator with a cutoff scale of 200 GeV. There are a number of problems with this statement. One, of course, is that why am I constraining a dimension 8 operator when the new physics could have effects at much what it could give dimension 6 operators. Why would the new physics only give an effect at dimension 8? And the other is that this naive limit of 200 or 300 GeV is really quite low compared to the typical momentum transfer for processes at the LHC. So in fact, if we look at, for example, the momentum transfer in this Mono-Higgs event, this is the distribution from dark matter, from the dark matter signal. It's all peaked, it's a dimension 8 operator, so it grows rapidly with energy, and it's all peaked at very high values of the momentum transfer, which are much larger than this cutoff scale. So this assumption of a contact operator is no longer useful at those scales, because it's much lower than these momentum transfers.
Are you sure? I mean, if you define that lambda by basically putting a coefficient of 1 in front of that operator, right? But that operator will actually violate unitarity at some scale above lambda, typically, more like maybe 4 pi lambda or something like that. So are you really sure that it's, maybe, in that case, you would have to assume that the underlying theory is strongly coupled, but it still makes sense in that case.
Yeah, so we tried this 4 pi lambda kind of, so the question is, what value of the momentum transfer should I compare with this? And so we tried setting a constraint of 4 pi lambda on this momentum transfer. So what we did here was say we can be conservative and assume this is still valid up to 4 pi lambda, the momentum transfer. We just keep all those events, throw away all the events above that, and say that's a conservative estimate of how many signal events we would get in that case. And you can do that as a function of the cutoff scale, and so you start to see that for lower and lower cutoff scales, of course, the number of signal events you get will slowly decrease because of this restriction until it drops off at some point just because you no longer have any events satisfying that. So if you do that, you still get some constraint, which is this shaded region. So it's not all bad for low masses. You can still get a reasonable constraint. If you were to make that stronger and change it to 4 lambda, you would get this much smaller region. Yeah, so this dashed line is basically the...
And is 4 pi lambda the scale where that operator violates unitarity? Is that the right?
Well, so I guess the other problem is that this is some dimension 8 operator. We don't even know how to UV complete it and say what the appropriate number is here.
Right, you could just compute a tree-level scattering amplitude from that and see if it satisfies unitarity.
Oh, you mean compare...
Tree-level unitarity balance.
Yeah. So we have that, but we didn't do the exercise to see what number should come up there.
Okay.
Usually a higher order operator would be worse. Take more power, like the inverse of power spec,
Yeah.
in order to set the boson lambda.
I see,
It would
yeah.
be even worse. However.
Okay.
I mean, if some of those lambdas are balancing derivatives, then it's not actually 4 pi lambda, it's probably lower than that. That's what I'm asking. So, anyway, the truth is maybe somewhere between you two.
Okay. So because of these difficulties in assuming it's a contact operator, this has led to work on simplified models. But before that, let me just say, studying these contact operators is useful, but because of this problem of the momentum transfers, you have many events appearing to violate this unitarity. So this is a plot showing what fraction of the events are well below some condition on the momentum transfer. And you really, what's been seen is that if you want it to be 90%, you need cutoff scales of order a few TeV, which is roughly what you might expect anyway. However, in another sense, the effective field theory limits are conservative because if you do have a new mediator, it could be produced on shell, and that actually leads to much larger cross-sections. So you can do all these different exercises of looking at what momentum transfers are allowed, or you can just go to one of these simplified models by putting in the new mediator. So rather than putting in a contact operator, you assume that there's some new Z prime or some scalar that could be produced on shell. The couplings of the new particle with the quarks and the dark matter, as well, are related to the mass of the scale for your contact operator. So there's a lot more data now, or there's a little bit more data now, which is your two couplings in your masses and your mass. But now you can accurately model the region where if you have order 1 couplings here, and you have, TeV scale Z prime. So these are known as S-channel simplified models for just simple reason that you're producing a new particle in the S-channel. This slide is to illustrate a number of lessons from looking at these Z prime models. So one is that the Z prime can go back into QQ bar pairs. So once you include new mediators, typically other constraints become more important. So in this case, dijet resonance searches become important depending on the ratios of the coupling of the Z prime to the quarks versus the dark matter. The other lesson from looking at simplified models that we're starting to see is that the mass ranges are very important, of course. So this plot is meant to illustrate how the effective field theory limits, or the limits for making that assumption, compare with the limits you get if you put in this new mediator. So this is coupling versus mediator mass with some assumption about the ratios of the couplings. And in the high mass limit, you do get good agreement with the effective field theory bound. In this intermediate region, your contact operator limit isn't terribly wrong, but it doesn't look very much like the actual limit, because the actual limit's coming from the region where the Z prime is produced on shell. And then finally, you have this region where the effective field theory is not valid at all. You have a light mediator, and their constraints are much, much weaker. So these are some general lessons. Tchannel, there's another set, which is the Tchannel simplified models. Here we have a new mediator in the Tchannel being produced with the dark matter. There's only one coupling in this case, which is this coupling. And now because, again, we're going to assume the dark matter is the gauge singlet, the mediator has to also be charged under some standard model gauge group. So I'm just going to briefly describe one example of a model. So this is a top flavored model. So the dark matter is coupled here. This is dark matter coupled to right-handed top quarks, plus a new mediator, which has hypercharge, for example, is charged. So I just want to mention a few words about this model, because I think it's also interesting in this case, because we were able to, so our paper, we connected this simplified model with just where you can just focus on the phenomenology with one additional particle. You can also connect that with some of these top-down approaches to dark matter model building. So the idea is you can get this kind of this simplified model by looking at a SUSY scenario where you introduce a dark matter supermultiplet. This dark matter supermultiplet could transform under the standard model of flavor symmetry, and in fact that flavor symmetry can stabilize the dark matter. The structure of the couplings in this SUSY setup, in this MFV SUSY setup, can also give you the right hierarchy of couplings and mass splittings, such that your lightest, such that the lightest particle in this dark matter multiplet couples mostly to tops. So so that's all I want to say about that. I think it's a very interesting setup, so I encourage you to look at that if you are interested. But let me just say some words about the phenomenology. So now the plots become, or the parameters become, the mediator mass, the coupling dark matter mass, and again you can look at the interplay of direct attention and relic abundance and collider constraints. So this region is shaded out because I need the dark matter to be lighter than this new mediator particle. The collider constraints are coming from pair production of this new mediator because it's colored because it's coupled to tops. So you can have colored production of the new mediator, which decays to top plus dark matter. And that looks a lot like a stop, so that gives you something like the stop search constraints here. There's a relic density line. The dark matter can annihilate through this mediator again to TT bar pairs, and that annihilation will set the relic density. And there's also direct detection. This is through one loop there's a one loop effect with a mediator in the loop and an exchange of a Z or photon. So this can lead to scattering off of nucleons. So that leads to, this is the most recent Lux constraints in this case. So if you look at this plot, it doesn't look like the collider constraints are terribly relevant, but it does depend on the coupling. So I can change if the coupling is smaller, these direct detection limits will almost go away, and the collider searches are the most important way to look for this kind of model. So this is just illustrative. There are many different ways to do this. This one is the paper by people here. The main points are that there's been a lot of work in expanding the scope of dark matter collider searches in this direction by looking at these Tchannel mediator cases. In addition to the example I presented, which just had fermion dark matter, again you can do this. You can make all these choices of fermion dark matter, scalar dark matter, and see what you get. So the main point I want to make here is that a lot of the searches are very SUSY-like because you're including a new colored mediator, but the signals are not exactly the same because you have this freedom, and also the kinematics are not exactly the same as the SUSY searches. So I think a lot of this is very useful because it's helping us push the SUSY searches beyond just the assumptions made in that come down from SUSY. Okay. So the last few minutes, I want to mention a simplified model for Monohypes. So all the contact operator, now a lot of the work is in building simplified models for these contact operators. Can we do it also for this Mono-Higgs signal, for example? And if you look at this dimension 8 operator, it looks quite ugly and it's difficult to UV complete. So instead of UV completing, trying to find a UV completion or renormalizable interaction to put here, we decide to generalize this diagram. So what that means is that instead of the Z, I now introduce a Z prime. The reason I did that is because the Z prime can now be on shell and decay to a Higgs plus dark matter in comparison to the Z. And then I need a coupling that produces dark matter. So I can't just put the dark matter at this vertex, but I can put in if I put in a pseudoscalar, that can decay to the dark matter pairs. And this pseudoscalar is very natural if there's a 2 Higgs doublet model where one of the Higgs could be charged under the Z prime. Then this diagram is automatically there. So the ingredients of this model are a TeV scale Z prime and type 2 Higgs doublet model. There are some constraints on this model, mainly again from dijets, because the Z prime can decay back into quarks. And there's also an issue of ZZ prime mass mixing, but I won't get into that. The main thing I want to say is that there is a potential Higgs plus missing energy signal in this model. There's actually two sources of it. One is from the dark matter signal, which is when the Z prime decays to the Higgs plus the pseudoscalar. Pseudoscalar Higgs decays to the dark matter. There's also a mono-Higgs from the Z prime decaying to a Higgs plus a Z. That also exists. The Z can go to neutrinos. And in parts of the parameter space that can be slightly, that can be more relevant. Okay, so for this model, we just explored, is it possible to find parts of the parameter space, or is it generic to get a detectable Higgs plus missing energy signal? And the answer is it's somewhat difficult. It is possible, but it's also difficult. So the parts of the parameter space where we found the most promise were at intermediate regions of this Z prime mass. At high masses, the LHC constraints on dijet resonances are becoming very strong. And also at low tangent beta. And that has mostly, again, to do with the constraints I mentioned 2 slides earlier on the ZZ prime mass mixing. So you can, these are the, you can get the ATV exclusion regions from the BB bar channel, and also look at the diphoton and BB bar reach.
If you just decided that your Z prime was, let's say, a scalar, then you wouldn't have those constraints. You wouldn't have those sort of precision constraints with the Z.
Yeah.
Would that open up more parameter space, or would something else watch that?
Yeah, we haven't looked in detail at the scalar case yet. So, yeah, I just don't know right now. Okay, and one other ingredient, I'll just say that you can get the pseudoscalar decay to dark matter. You can get an order 1 branching fraction in some sort of singlet doublet type model. So it's a work in progress, but let me just say it is possible to write down a model where you get that order 1 branching fraction of the dark matter to the pseudoscalar. Pseudoscalar to dark matter. Okay. So since my time's almost up, I want to conclude by just discussing what happened or what's been happening in this field of monojets. So whether or not you like the particular models I've been presenting, I think this work has led to this work has been expanding the scope of dark matter searches, collider searches. So it started with a simple framework of just looking at contact operators. These operators inspired people to do many mono-something type searches and look at not just operators coupling to quarks and gluons, but many other things. The realization that these operators had, or the effective field theory limits had some limitations, led to studies of simplified models with additional new mediators. And for example, there's the S-channel type mediators I discussed and the T-channel type mediators. And this work has been very interesting because we see as we've been exploring these models that there is a need to develop more dedicated analyses for the simplified models considered here. The initial work has been mostly to recast SUSY type searches, but we've been seeing that that's not entirely sufficient. So for example, the 2 cases I was discussing are the mono B search, where we looked at single B jet or 1 or 2 B jets plus missing energy as a probe of certain kinds of dark matter interactions. Also as a probe of dark matter interactions with different flavors of quarks. And there's also potentially very interesting signal, especially for 14 TeV LHC, which is a diphoton from a Higgs decay plus missing energy. So we've seen starting just from monojets, we've seen lots of different new signals for dark matter and also different kinematic regions of existing searches for dark matter. So I think there's many opportunities with the LHC run, the next LHC run, to keep keep looking for ways to use the data to look for dark matter. So again, as I said, whether or not you like these models or what people have explored so far, I think it tells us that we need to keep looking and keep seeing where we can expand our scope. So, thank you.
More questions for Tongyan? So, yeah, if not for now, thanks Tongyan again.